since this is my first time presenting to the lab, just a disclaimer that I'll probably mostly be focusing on motivating the research, as well as discussing some of the challenges in state of the art. So today I'm going to be discussing my work over the past few quarters during my AA290s, which is deep learning for exoplanet detection and characterization. So like I mentioned, I will start with motivation and challenges of this research, as well as discussing the state of the art. And then I'll go into kind of the research objectives for this larger research project, as well as give some preliminary results. And then I'll conclude with some future work and the impact of this research. So getting right into it, why do we care about exoplanets? So exoplanets are actually very foundational to a lot of central questions in astronomy and astrophysics, from the very philosophical questions of, are we alone? Is there other life out in the universe? To also more practical research in terms of understanding our solar system in the context of a universe. So understanding our planetary distribution, understanding how unique our sun is. All of these questions can kind of be addressed by delving into the formation and characterization of exoplanets. So the past few decades has seen kind of a proliferation of exoplanet discoveries, and space-based telescopes and satellites have been really foundational in a lot of these discoveries. In particular, the Kepler and K2 missions were responsible for, I think, over 3,000 of the exoplanet discoveries of the confirmed around 4,000 exoplanets that we have so far. Hubble and Spitzer have also been foundational in confirming a lot of the discoveries from Kepler, and the Transiting Exoplanet Survey satellite is a more recent mission that has again been foundational in discovering a lot of new exoplanets out in the universe. And so most of these discoveries have been through indirect imaging methods. So when we're talking about indirect imaging methods, we're referring not to directly observing the exoplanet, but rather making observations or measurements of the effect of the exoplanet on its host star. So two of the more popular methods are the radial velocity method, which quantifies what we call the wobble in the host star, as you can see in that top right animation. And so by quantifying the wobble of the host star, we're able to back out the gravitational influence of the exoplanet and therefore confirm its existence in orbit around the host star. Similarly, the transit method has been used both by Kepler as well as TESS, and it makes measurements of the host star's luminosity and the periodic dip in that luminosity as an exoplanet crosses over or transit over the star. So although these indirect methods have been critical in kind of the discovery of so many exoplanets over the past few decades, they don't give us a ton of information about those exoplanets because they are indirect measurements. And so where do we go from here? We know of the existence of thousands of exoplanets, but we don't really have a way of studying them with these methods. So every decade, there is an astrophysics decadal survey that comes out that roadmaps the largest and highest priority research areas in the astrophysics and astronomy community. And last year, they released the 2020 Astrophysics Decadal Survey. And one of the key priorities that came out of that was pathways to habitable worlds. So it's not enough just to know that the planets exist, but now we really need to delve into studying and characterizing those planets, which again is just not possible with indirect methods. So this kind of motivates our transition to more direct imaging, which allows us to characterize the atmospheres of planets and detect for biosignatures, which will allow us to determine whether or not those planets are capable of supporting life. So if direct imaging is, enables us to get so much more information, why is it not something that we have used more frequently? And the reason for that is the biggest impediment to direct imaging is the fact that the glare of the host star is orders of magnitude brighter than the exoplanet itself. And so in order to take direct photometric data of the exoplanet, we need to suppress the light from the host star in order to increase the contrast of the image of the exoplanet against the background. And so coronagraphs and star shades are kind of the most promising starlight suppression technologies. Coronagraphs are internal to a telescope And star shades, as represented in this video and image on the right, are external occulters that suppress the starshade light and allow you to increase the contrast to detect the exoplanet signal. And starshades have been shown to produce higher contrast. They can suppress the host star light by up to 10 to the 10 orders of magnitude. So despite this promising performance, there are still significant challenges associated with direct imaging. And that comes mostly in the form of several sources of noise that confound the exoplanet signal in the image. So a few that I just want to touch on really briefly here, because they'll come up again, is speckle noise and the point spread function, which are functions of your instrument, as well as exozodiacal dust, which is a source of astrophysical noise. So the speckle noise is caused by aberrations in your telescope that creates what we call this speckle pattern in the resultant image. Point spread function is the impulse response of your optical system, which causes this blurring in your resultant image. And then exozodiacal dust is carbon dust that has been created because of planet formation or collisions. And although it in and of itself is an area of study, we want to learn more about exozodiacal dust in the context of exoplanet discovery. It confounds the images by diffusing a lot of that light throughout the image. So just expanding on this a little bit more, the result of all of these noise terms, which those three that I just mentioned are only a few sources of noise in an exoplanet image or a starshade exoplanet image. But the additive nature of all of these noise terms results in a very low signal to noise ratio. So the signal of your exoplanet in your image is buried under, several sources of noise that are often spatially and temporally variable and have a similar scale to the signal itself. So really, to drive this point home, I think a visual representation is the most accurate or the most impactful. So here are two representative starshade images. These are simulated images generated by Sister, which is a simulation toolkit that I'll discuss a little bit more in detail later. But for now, you can see that these resultant images are very low quality, right? You can almost count the pixels in these images. And even being generous and imparting some expert knowledge on you, I'll let you know that there are 2 exoplanet signals in the left image, and there are 3 exoplanet signals in the right image. So even with that knowledge, it's very difficult to disentangle where those signals are in the image themselves. So if we annotate these images a little bit, this reveals the red boxes reveal where those exoplanet signals are in the image. And then I've also included an annotation of some of the more significant noise terms in these images. So of course, those bright spots in the middle are residual light from the host star. So even while the starlight or the star shade suppresses the starlight by a significant amount, there is still residual light that makes it difficult to disentangle the signal of the exoplanet from the light from the host star. Additionally, I'm not sure if it's fully visible on your screen, but there are 2 different models for exozodiacal dust that are often used in these images. So one is the resonant exozodiacal dust in the left-hand image, and that you can see kind of causes this more diffused light further out radially from the host star, versus on the right-hand side, we have the smooth zodiacal dust, which is a more compact disk shape. So hopefully this makes it clear that even with the promising performance of these direct imaging techniques, there's still a significant need for post-processing capabilities in order to actually extract relevant information about exoplanets from these images. So moving into kind of what are those state-of-the-art image processing algorithms. So the state-of-the-art image processing for direct exoplanet images is kind of a pipeline of 3 main steps. So the first step is background estimation and removal, where you have your input image, you estimate the background and subtract it off from the image to reveal a residual image. And then that residual image is transformed into a signal to noise ratio map via a matched filter, which is a linear filter that aims to increase the signal of the exoplanet in the presence of like a stochastic noise term. And then finally, once we have that signal to noise ratio map, it's a matter of kind of identifying the brightest sources in that signal to noise ratio map and labeling those as your detections. So diving in a little bit to the background removal step, because that is often the most difficult portion of this pipeline. There are a few state-of-the-art algorithms that are used to estimate and remove the background. So one is the locally optimized combination of images, or loci. And then there's the Karhunen-Loewe image projection, or CLIP. And so both of these algorithms at their core are using principal component analysis to estimate the modes of variance in the image. And then based on how many of those modes you choose to use, it subtracts off more or less of the background. The issue with this is that, it's manual tuning that enables how many modes you are using. And the more modes you use, the more noise you capture, but also the more of the signal you end up capturing. So you can see in that animation on the right, that's the residual image based on how many modes you are using to subtract off the background image. So you can see as you increase the number of modes, the image becomes more and more sparse. The other difficulty with a lot of these state-of-the-art processes is that they require specific observational techniques in order to even process the data. So the data needs to be collected according to a specified regime in order to be able to calibrate the background from the noise. So the three most popular are angular differential imaging, spectral differential imaging, and reference differential imaging, all of which use some type of variation in capturing the same scene in order to calibrate the data. So for angular differential imaging, you take an image of the same scene at different angles. With spectral differential imaging, you take the same image with various wavelengths. And with reference differential imaging, you approximate the point spread function of other host stars and then apply it to your image in question. So as we've kind of touched on, a lot of the state-of-the-art image processing pipeline is extremely laborious, requires expert knowledge of your data set, requires specific observational techniques. So it makes it this application prime for implementing machine learning. Convolutional neural networks have been extensively applied to object localization problems, from autonomous cars to robotics. And of course, here in SLAB, we've used them extensively for spacecraft pose estimation with Jeff's work. So the application specifically to exoplanet detection, however, has been very limited. And this is primarily due to the lack of data that we have to train a network. And so convolutional neural networks require extensive, diverse data sets in order to train the parameters of the network. And since we don't have access to images where we know for sure where the exoplanets are located, it makes it very difficult to train a CNN accurately. So in the interest of time, I'll briefly explain how CNNs work. Of course, this is an entire area of research in its own, so I'm happy to discuss further offline. But basically, similar to how the state-of-the-art algorithm uses the principal components to approximate the background or common features of an image, a CNN uses convolution layers to learn features of your image via parameter learning. And so it passes an image through several convolution layers and makes a prediction. It then compares that prediction via a loss function to some ground truth labels, and then back propagates to increase or improve the parameters of the model. And so one thing additionally to touch on here is that, like we've mentioned, CNNs require comprehensive labeled data sets, and these are very difficult to come by in terms of actual true spaceborne images. And so a state-of-the-art and very new addition to this realm is the Starshade Imaging Simulation Toolkit for Exoplanet Reconnaissance, or SISTER. So this is a JPL developed simulation toolkit that is able to provide synthetic, specifically starshade images that accounts for several of those astrophysical, optical, and sensor noise terms that I discussed earlier. And this is really foundational in enabling a lot of the research that we're discussing here. So by leveraging SISTER's capabilities to develop synthetic images, the long-term goal of this research is to develop and train CNNs for both exoplanet detection, so detecting and locating an exoplanet in an image, and even larger than that, the characterization of those exoplanets, namely being able to extract the spectra of the planets. So this is obviously a very large goal. And so the more immediate sub-goals that I've been addressing over my 290s in the past few quarters is to really just understand the capabilities and constraints of applying CNNs to exoplanet localization, and then comparing that to the state-of-the-art image processing algorithms, or the pipeline that I showed earlier. And so really quickly, the data set that I have been working with is generated by SISTER for an ongoing Starshade Exoplanet Data Challenge. I am not participating in the data challenge, but because the data set is publicly available, I have been able to use their data set in order to train a CNN and apply a state-of-the-art pipeline to it. So a few things to note really quickly is that the entire data set is around 1,400 images, but only 10 unique exoplanet scenarios. And the rest of those images are generated by varying some of those noise terms. So on the right here, you can see this is the same image or the same exoplanet scenario with different noise terms. So varying the model of the exozodiacal dust and the density of the exozodiacal dust, as well as modeling the contrast that would be enabled by the starshade. And so the convolutional neural network architecture that I have been using is a bounding box neural network, which is YOLO v3. So YOLO, but the third version. And YOLO is kind of the state of the art in bounding box regression. It uses the third version specifically uses a generalized intersection over union loss function, where intersection over union is a common metric used in localization tasks, where it calculates the intersection of the bounding box of your prediction versus the ground truth label over the union of those two. And so that's what is used to assess the performance of the CNN and then backpropagate out to alter your parameters. I used a 80-20 training testing split, which is pretty standard, as well as 200 epochs with a 32 image batch size. YOLO v3 is a very large network, about 50 million parameters. So future work will definitely include streamlining the architecture to minimize the number of parameters used. The state-of-the-art pipeline that I used was piclip. So piclip is an open source Python library for exoplanet detection and disk detection. It is an implementation of the CLIP algorithm I discussed earlier, which uses principal component analysis to estimate the background. It also includes methods for matched filtering and planet detection, so you can really complete the full pipeline of exoplanet detection using piclip. It, like I mentioned, does require that the data be formatted in one of those specific observational techniques. So because of this, the data set that I'm using had to be split into several subsets in order to be able to apply piclip to this data set. More specifically, I concatenated the images, the same image for a 425 wavelength versus a 615 wavelength. And that was concatenated into a 2-channel image to then apply piclip using spectral differential imaging. Through manual tuning, I found that 15 modes or 15 basis vectors was adequate for estimating the background. So moving into the results, there are 4 main parameters that I was looking at: the precision and the recall, which are respectively kind of a good way to measure over prediction and under prediction. So specifically for recall of the predictions that, or sorry, for precision of the predictions that you make, how many of them are true positives, versus for recall, how many true exoplanet detections are you missing in the image. IOU we've already discussed, and then the other metric that was used was the Euclidean distance. So the Euclidean distance of the centroid of the ground truth prediction or the ground truth label versus the predicted label. And so I currently only have the YOLO v3 results for these metrics, and that's unintentionally indicative of the time intensity required with piclip, because I had to break piclip into several data sets, and each data set requires going through the pipeline individually. So for YOLO v3, there's a few things I want to point out here. One is that the recall is significantly higher than the precision, which means that the CNN has a tendency to overpredict, but when it does make a prediction, it's right about 85% of the time. And the other metric I want to point out here is that the mean Euclidean distance between the centroid of the true exoplanet and the predicted exoplanet is about half a pixel, a little greater than half a pixel. So state-of-the-art centroiding algorithms are able to get within the accuracy of 1/20th of a pixel. And so we're far off from that, but directionally indicative of the performance of the CNN. Another thing to mention here really quickly is that because this data set is so small, significantly smaller than what is actually required for training a CNN, we are expecting that a lot of these results are due to overfitting. So perhaps a little bit more interesting to look at is a input image. So the same image and the piclip detections versus the YOLO detections. So a few things to note here. Again, this is the same image, and just looking at the detections for both algorithms, the green represents the ground truth labels and the red represents the predictions. So you can see both piclip and YOLO overpredicted. Both of them got one planet correct, but not the same one. So that's just an interesting, I guess, glimpse into some of the preliminary results that we're seeing here. So again, this was a very limited analysis so far, but what it does show is that CNNs are very capable of significantly reducing the amount of expert knowledge required prior to post-processing. So like I mentioned, piclip requires analyzing the data and separating it out into subsets in order to be able to estimate and remove the background from the image. And so while CNNs are time intensive on the front end during training, that time really falls off with the speed of inference, versus for piclip, it's time intensive throughout the entire pipeline. However, despite this, both CNNs and the state-of-the-art have strengths in image processing. And so future work is going to look into where the two can inform each other. So again, just touching briefly on the future work of this research. And of course, again, this was a limited scope analysis. So there needs to be significant work done to improve and expand the data set that is being used for both the CNN, as well as to compare more thoroughly to the state of the art, as well as additional optimization and validation. Finally, I just want to conclude with some of the impacts of this work. So in the realm of exoplanet research, we've kind of discussed this, but if we're able to extend the CNN to being able to characterize the exoplanet spectra, that is going to have a huge impact on exoplanet science and what is possible to learn about those planets. And again, this is kind of a key milestone goal that has been released as part of the decadal survey and is a pretty prominent research area in the astrophysics community. But even more than that, these problems that we're solving or addressing here are more applicable to space domain awareness in general. So the problem of exoplanet detection and characterization is very analogous to resident space object characterization. So determining the attitude and the orientation of resident space objects or of unresolved space objects. So with that, I am open to any questions.